Okay, welcome back, everyone. How are things going? Good. So I saw a few of you, actually a fair number of you, in my office hours this morning. That's good. Don't be afraid, though, to use other people's office hours. For instance, after class, one of our TAs, Debbie, has office hours today. So every day there's 4 or 3.5 hours of office hours dedicated to this course. Does anybody have any questions they want to ask me?
Going to pub night?
Am I going to pub night? When is it?
Tonight, isn't it?
It's tonight. Oh.
5:30.
Yeah, no. I'm not going to pub night. Sorry. Somehow I missed it, and I was at a pub last night, so. Yeah.
For question 2 on the assignment, you say imagine each line is numbered.
Yep.
Are they numbered?
No. You have to imagine it. Yep.
Update on the grading server?
Dabby has it up in beta form. He'll open it up later today after his Japanese class. And that means you'll be able to test your implementations, but not do the second part, which is testing your tests. So real soon now. Any other questions? No. Yes?
Could you elaborate on question 3?
Elaborate on question 3. This is the minus 67 question? Yeah. Okay. So I was very precise when I wrote this. So you have a line, and it has, or you have a file or an input rather, and it has millions of lines. And basically what I want is that if one of those lines is a blank, then I want you not to output that line, but to output the line 67 lines prior to that one. Okay? So in the end, the number of things that you output will be just the number of blank lines in the input file. Okay? So in general, you don't output anything unless you see a blank line. Then you don't output that blank line. Instead, you output something that was 67 lines before. People are confused by this last sentence in the question that says, in this way, the number of lines you output is no more than the number of blank lines in the input. Why not no more? Why not equal to? Well, because if you have a blank line within the first 67 lines, that doesn't do anything because there's nothing 67 lines before. So basically, for every blank line you have after the 67th line, you will output something. Yep.
For question 6, should we have to write any lines of code to do sorting, or should the collection do all the sorting for us?
You should probably use collections.sort, which we'll discuss a little bit today. That's the way I did it. Yep.
So if you have like 500 lines, and then let's say the 499 minus 17, so you do 499 minus 67 would be 432. Would it output that line 432?
You would output 432.
Yeah.
Yeah, just 432.
And then 432 is blank?
And then you output the blank. So whatever the contents of that line are, even if it's nothing, you output that.
So you don't want that sort of recursive?
No. Yeah.
So you output the line number of the line?
No, you output the contents of the line.
Okay.
Yeah. Yeah. Are you limited in the collections you can use? Not terribly, but there's really no reason to use any of the things that we've discussed. So there's no reason to use anything other than the collections we'll have discussed until today, basically. So today will be my last sort of Java collections framework discussion. After that, you know everything you need for the first assignment. I don't know what else you would use. Somebody mentioned vector. Don't use Java vectors anymore. They're more or less deprecated. They're bad. Yeah.
Okay, for question 3 again, what happens if you got a blank line and then 67 lines later there's another blank line?
Then 67 lines later, you will print out that first blank line. Yeah. Okay. Good. So where were we last class? Well, we had seen all the interfaces in the collections framework. There's not too many of them. And we were discussing, let's say, the most common implementations of those interfaces. And so we had looked at the list interface and saw that actually the most commonly used version of a list is the array list. They're easy to make. You can add things to them. We saw that the array list, I mentioned this both when I sort of talked about it and we did an experiment, that adding things to the beginning of an array list is an expensive operation because all that's happening is the list is stored in an array starting at position 0. If you put something new at position 0, everything else has to be shifted out of the way. And so that's expensive. On the other hand, adding to the end of the array is cheap. There's nothing has to move to append to it. And that's so common that the list interface actually has 2 versions of the add operation. One takes only 1 argument. It's the thing you're supposed to add, and it just puts it on the end of the list. And the other one takes 2 arguments, the index of the thing you're trying to add and the value of the thing you're trying to add. And that can put it anywhere, but you have to be aware that adding to the beginning of an array list is slow. And we had done this little short example list where we had a few of the characters from Big Bang Theory in it. So adding and removing. And we looked very quickly, we looked at the set interface and what is the most common implementation of the set interface. It's called the hash set, which implements sets using a data structure called a hash table. It's super, super efficient. Probably this is the one of the most used data structures after lists for anything. The thing you need to know about a hash set for now, until we see how they're implemented, is that you can add things, remove things, and check if a hash set contains something. And all of that time that those operations take is independent of the number of elements in the set. So it doesn't matter if there's 10 elements in the set, doesn't matter if there's 1 billion elements in the set. It all takes time that's independent of that, and it's actually very, very fast. Okay, and I want to maybe demonstrate this. So let's make sure we have code that compiles right now. Okay, so so there's a set that we made with these things, these names that we added. One thing to look out for with sets is, yes, fast for adding, fast for removing. They have no notion of order, so if you iterate over them, the only thing you can count on is that everything in the set will come out exactly once in this iteration, but you don't know what order it will happen in. So let's make a set of integers. We'll make it a hash set. And let's add a bunch of stuff to it, maybe 1 million elements. And so we'll add, for I from 0 to 1 million minus 1, we will add 2 times I to the set, so we'll only be adding even integers to the set, and it's going to be a million of them. We'll see how fast that is. So more or less instantaneously. Between creating set and done, there's just a tiny pause, so that's how long it takes to add 1 million elements to a set. We can look for how quickly we can check if things are in the set. So we will search in the set. And what will we search for? We'll search for 2 million values. Half of them are in the set, half of them are not in the set. Okay. Whoops. Contains. So contains will return this VGA cable is not doing well. Contains will return true or false depending on whether or not the thing is in the set. Where are we? Contains I. So let's see how long that takes. Creating set, searching set, done. Again, very fast. There's not really so that's 2 million searches that take place in, I don't know, a quarter of a second or so. And we can clean the set out, deleting everything. See how long that takes. Again, super fast. The deletion is actually really fast as well. Okay, so these things are really good, really fast for this kind of stuff. If a set solves your problem, use it. It's going to do well for you. On the other hand, lists not so good. So if you remember up here, we made a list that contains 1 million elements also. And if we were trying to do something similar, so here we have a list that contains the integers 0 through 1 million minus 1. We can ask a similar question. Does the list contain, we can do a bunch of searches asking if it contains these things. And well, we're hung, it looks like we're hung here, and that's because, so that's adding the integers to the list. And now searching. So where we get stuck is on the searching step. Okay, so trying to look up things in a list is painful. Lists don't organize themselves to make it fast to check if things are in the list. So every time you ask, is the integer I in the list, it basically starts at the beginning looking for this integer I. This list has 1 million elements, so that takes a while. We could, if we want to keep track of the progress, we could, print some progress indicator. So let's say if I mod, let's say 10,000, 0. Why? Yeah, why not? Okay. It really feels like the keyboard is killing the cable. Okay. So that's still going. Let's kill it, try again and see how it does, how it progresses. So we'll put a little progress indicator, an X, every time we do 10,000, we get through 10,000 things. Does anybody want to guess how the progress will look? So we created this list with 1 million elements, and now it contains the elements 0 through 1 million minus 1. And then we start asking it, is 0 in the list? Is 1 in the list? Is 2 in the list? Is 3 in the list? And so on. That seems to be taking a long time. It didn't finish in the time that I was fooling around here. What are the progress indicators going to look like? They're just going to tick off slowly? Yeah.
It's going to slow down over time.
Yeah. So I'm going to guess that actually the implementation of searching in that list is sequential search starting from the beginning. So actually, the first ones should happen fairly quickly because we're asking if things are in the list, and they are in the list, and they're near the beginning of the list, so they should happen quickly. But then as this progresses, it's going to take longer. So let's see. So there's our X's. A few of them came very quickly, and indeed, now they're getting slower and slower because searching for the value I in the list basically has to look at I elements before it finds it, and I is going all the way up to 1 million here. Okay. So we're expecting 100 of these X's before we're done. Yeah.
How does the contains function work for a hash set?
So, well, that's the topic of hash tables that we'll talk about later in this course. But basically, a hash set stores things in an array, and it essentially, what happens is when you put something in it, it gets a random address in that array. Okay, and so it gets its own spot in this array. And so when you come and search for it later, you do that same random looking function, and you go and look for it in the same spot. When you search for something else that's maybe not there, you do that random function, you look in the array at the place where it told you to look, where if it is there, it's going to be stored there, and either you find it or you don't, but in either case, it's not present. In fact, that's a bit of a simplification. What's really happening is it's an array, and each element in the array is a list of all of the things that are stored there, but there's only a couple of them typically, or none. So basically, in constant time, it takes this problem of searching a giant set and reduces it to searching a list that only has a few things in it. So I'm not going to wait for 100 X's. We'll just give up on that. So the moral of that is if you find yourself calling contains on a list, don't do it. Change to a hash table, or if you need order and you need contains, then store your data both in a hash table and in a list. Okay. Any questions there so far? You know how to use these things? Any of these? Yeah? Which one would be worse on memory? Hash table probably uses a little more memory than a list, but it's close. It's not orders of magnitude or anything. It's just small constant factors. Yeah.
If we were to look at the API and see what methods we can use, we have to look at the one for set or hash set.
The only ones you'll need are the ones that are from the set interface. If you find yourself doing particular things with hash set, then it's probably you're doing the wrong thing.
It's not for other types. When I look at the interface and try to use a method from there, it's telling me I couldn't because it's the implementation.
No, you can always use a method that's in the interface, but you can't always use a method that's in the implementation. So for example, if you look at the way I've been doing things here, when I create one of these things, I create a variable whose type is set. So that's an interface. So that means Java immediately forgets, I assign it to a hash set, but Java immediately forgets that this thing is a hash set. And hash sets have some methods that are not in the set interface. But at this point, it immediately forgets that, and the only things that I'm allowed to use with this are the interfaces of the set method. Some we discussed, and some you can look up. But in general, this is not a bad way to do it, because it guarantees that if later you decide that hash set was really not the right implementation, you wanted some other kind of implementation of sets, it's just a one-line change. You just change the right-hand side of this thing. The rest of the code will continue to work because the rest of the code was only using things in the set interface. Okay. Good. And we saw, I don't know if I showed this to the whole class or just one person after class, sorted sets. So the standard implementation of a sorted set, remember these are just like sets except they keep their things in sorted order. The standard implementation of a sorted set is what's called a tree set. So it uses a binary search tree, which we'll discuss in this course, to store its elements. It's not quite as fast as a set. It's still pretty fast, but not quite as fast as a set because it has to do extra work. It has to care about preserving this special order, unlike sets, which can do whatever is the fastest thing. And I think I can show you, if I remember correctly. So my set that contained these characters was called set. Okay, so let's print the contents of that. So there's usually, I think, all of the collection classes have this convenience method, add all. which is useful when you're trying to fill a collection with the contents of another collection. So here I create this new empty sorted set, and I say add everything that's in set. I could have equally passed in a list here or any other number of things. And here's my sorted set, and notice now that the names appear in a very specific order. They are sorted lexicographically, which really sort of means alphabetically in the usual dictionary order. The only thing that makes them a little bit different than dictionary order is all the uppercase letters come before all the lowercase letters. So, so if I put into this thing something like you might be expecting this to show up near this crypt key, but actually it shows up before everything else that starts with lowercase letters. And basically this is sorted using the ordering defined by string compare. Yep.
So for every time you add that sorted set, does it sort?
No, it's much more clever than that. So, I mean, if you're now thinking about implementations of sorted sets, and you're discovering, let's say, the most obvious implementation would be you store the elements in an array, and when somebody asks you to add something, you maybe append it to the end of the array, and then you sort the whole array. So that would be very slow, because if the array contains 1 million elements, then you add one more, then you're sorting 1,000,001 elements. Tree sets are much more clever than that. They use a binary search tree on these things, and basically are just inserting this thing into a binary search tree. Yep.
Is the speed of add all dependent on the collection that you're moving from to?
Well, add all essentially just repeatedly calls add on whatever so it depends on a few things. So it calls add on whatever it is you're adding to. So hopefully that's a fast thing. And it also has to iterate over the elements of its argument. So hopefully that's fast to iterate over the elements of the argument. So that comes into play. Lists have another add all, which takes an index as well, and it adds the entire collection starting at that index. And that's actually more efficient than if you were just to add them by hand. So in an array list, for example, that does the smart thing, which is to make room for all the elements and then copy them into these locations, rather than insert one element, shifting everybody over, insert another element, shifting everybody over.
So otherwise it's pretty stupid.
It's pretty stupid, yeah. Think of it, except for the special case of the 2-argument version for array lists, it's just a for. It's just prevents you from having to write a for loop. Good. All right. And did I show you guys some example of tail set or head set or subset? No? Okay, so let's do an example. So remember, tail set, you give it it's a method in sorted set that says, give me everything that's bigger than or equal to some value. So my sorted set is a list of strings sorted alphabetically. So I could ask for everything that is bigger than or equal to Howie. And so what's going to be in there? What's going to be in that particular tail set? Yeah. So it should be Kripke and everything beyond, right? Because Howie alphabetically comes after Howard. So it's not going to include Howard. And indeed, it's everything that comes after Howard in this set. Now, I said that I couldn't remember whether this was inclusive or not, so let's just check that. If I give it Howard, it does indeed include Howard in the set. So it's everything that is greater than or equal to its argument that's in the set. Okay. Here's a hint for you. Pay attention. What's going to be in there now? Yeah. Same thing as the last one. Everything from Howard onwards. So Howard. I mean, if I ask for the tail set that starts at How, I get the thing that starts at Howard. Okay. That's something. That's a hint for the assignment. You can figure out which question it's for. All right. And then there were maps. So maps and sets, I said, have a lot in common. In particular, a map is storing a set of keys. It just happens that with each key, it's also storing a value. So here I'm creating a map whose keys are strings and whose values are integers. And not surprisingly, the implementation of map is essentially the same implementation as set. We use a hash map as the most common such implementation. In fact, internally, they're both using the same data structure, sets and maps, at least in the current implementations of the Java collections framework. So let's say, let's call that map, and we can do something like map.put, I don't know, Howard, and we can rate our characters on how much we like them. So on a scale of 1 to 10, how much do we like Howard? 6. Okay. And how much do we like Amy? 6. How about Leonard? Can't be 6.5. It has to be an integer. 2. He's not as lovable as some people think. Sheldon? It's kind of a, people have, nobody's on the fence about Sheldon. And Kripke, you all know who Kripke is, right? Yeah, 4, really that high? All right, so now I can iterate over this thing, and let's say for string s in map.keys. I think that's the right method. Okay, if I did this right, key set, that's what it is. Come on, guy. So if I did this right, this should print, actually give some nice printout of the mapping. So I iterate over the keys in the key set, and for each key, I print it, and then I print the value associated with that key using map.get. If we want, we can reassign these values at any time just by calling put again. I think we were a little bit hard on Leonard. So let's give him a 6. And it's fine to do that. What we can't do is do something like map.get some name that's not there. If we try and access a key that's not there, we will get what? I guess we just get null. I thought we would get a missing key exception, but it seems not. So if we try and get something that's not there, we get null, which usually leads to an error if you're not expecting it. Okay. Notice anything about this printout here? Anything stand out? Yeah.
Is it not ordered?
Again, same thing. It's not. There's no particular order. It's not the order we put them in. It's not the order that we. It's not any sorted order or anything. It's just whatever order was convenient for this this thing to store them in. And for a plain old map or implemented as a hash map, that order has no real use to it. And that stands out. When you say, give me the key set, you're getting a set of these keys that are not ordered in any way. Okay. If we want order, then we use a sorted map, which we can do. So So in that case, we could use a tree map. And if we do that, then we get a set. This is where we started printing things in order. We get this thing ordered alphabetically. Amy, Howard, Kripke, Leonard, Sheldon. Yep.
But if you wanted to order it by its value,
Aha. So you've been working on the assignment. So if you want to order it by its value, that's not the way these things work. Yep.
Is it appropriate to import Java.util.star?
Is it appropriate? Sure. I'm not. No one's going to dock you if you import java.util.star, and it saves a lot of going back up to the top of the file to add the class you forgot to import. Yeah. So your question was, well, what if I want this thing to be printed, but in some order that's not alphabetic order by the keys, but let's say numeric order by the values, and let's say descending numeric order by the values if you're being really specific. So you want to see the highest ranked character first. So how do we solve a problem like that? It's not what maps do. It's not. We have to go beyond maps. Yeah?
You can just flip so that the keys are the names and the values are the
Oh,
keys are the numbers.
okay, so the suggestion is that we invert this map so that the keys are the numbers and the values are the names. So is that going to work? Yeah?
Well, it won't work if you have 2 sixes. You have 6 mapping from 2 different things.
Yeah. So remember that the keys have to form a set, the values don't, and in this case, they definitely do not form a set. We have 2 sixes, in fact 3 sixes by the time we get to the end of this. So if we do this inversion, we're going to end up with a map that contains the keys 6, which will probably be pointing to Leonard, the key 10 pointing to Sheldon, the key 4 pointing to Kripke, and we'll lose Howard and Amy, depending on the order we put things in. But if Leonard is the last one we insert, then it's going to overwrite the other two. Yeah?
Because of the way strings work, string concatenation, I don't think it will work for the assignment, but you can add to the value associated with the number, just tack it on to the end. So you could add Howard to 6.
Yeah.
And then say the value associated with 6, add, for example, Amy to that.
Well, be careful because you're mixing strings and integers here, so that's an issue. Yeah.
You take all the keys, put them into a set, take all the values, put them into another set, and then just sort the second set, and then
But then,
just use the original map to have their corresponding, like their correlation and matching up thing, and then reorder it that way.
okay, so there's a suggestion that we take all the keys, put them into a set, or we take all the values and we take all the values and put them into a set. So what would that look like in this case? So, I mean, we already have the keys in a set. That's this Howard, that's the names of the characters, and so on. And then what would the values be? I think it's 6, 2, and 10, right? And 4. Okay. And And we can get them sorted if we use a sorted set. Okay, so now we've got this sorted set that contains these things. What do we do? How does that help us? Yeah.
You could look for every key amount that has
So you would say something like, in my map, I have these names. I forget who the other ones were. So now what? These all map to, the map takes these onto certain things. I forget what they were, but is this giving us, we have the values in sorted order. Does that help us in any way, really? Yeah.
Make it a statement and see what corresponds to that.
Well, so the problem is just sorting the values all by themselves doesn't really help me, because the map is set up that if I give you a key, I can quickly look up a value. If I give you a value, there's no nice way to quickly look up the keys that are associated with that value. In fact, the way that you can do it, but all that happens is you end up iterating over the set of everything. So it's kind of a slow operation. So what you want to do instead, and I'm not going to do it for you, is don't extract any of that. I mean, don't separate the keys and the values. Just get them all. So do something like, so remember, a map contains these things called entries. And so you can grab that list. And I'll show you how to grab the list, and then it's going to be up to you to figure out how to sort it. So let's take a list which contains map entries. A map entry is parameterized by two things. In this case, the map entries contain string keys and integer values. So this looks a little complicated now, but it's not terribly so. And I don't know, let's make that an array list. Easy to make a mistake here. Let's see that compiles. List map entry string integer. Let's call it my big list. Okay. So we declared a variable and assigned to it. So now we want to do something like my big list, add all, and we take our map, and we take everything in the entry set, and we put it into the list. Okay, so that seems to work. And now let's say for this is where you'll start to see that C++'s auto keyword is really helpful when you have to keep declaring map entry string integer repeatedly. So for everything in my maps, in my big list, so now I have a list, and this list contains all these entries. So let's just print them out. And so we say e.getKey plus Okay, so this second thing here is my is no longer a map that I'm printing out. This is actually a list of things, list of pairs of things, keys and values. Lists are things that we can sort, right? Everything has an order in a list. It's not in any particular order. We can ask Java to sort this thing for us. All we have to do is tell it how to sort it, and the way we want to sort it is by comparing values. Okay, so let's take a quick look at collections.sort. So one of the classes in the collections framework is a class called collections with an S. And it's not really a class that you ever make an instance of. It's really just a whole bunch of algorithms and things that you use to do stuff. And some of these algorithms, there's things like binary search for searching in sorted lists. There's some special things that you make, things for making copies of lists, but the ones we're interested in now are sort. So sort takes a list and sorts it into ascending order according to the natural ordering of its elements. And then there's another version of sort which takes a list and takes a comparator and sorts the list on the order that's defined by that comparator. So let's do a quick example of this. So we have a list. I believe it was called LELL. So let's remind ourselves of what was in there. Contents of L before sorting. Contents of L after sorting. Make sure we import collections. Okay, so this is what was in L before we sorted it. Stewart, Kripke, Howard, Amy, Leonard, Raj, Penny, Sheldon. That's just the order we added the things to that list. Then we called collections.sort on the list, and we get it in sorted order. Okay, good. If we don't want it in that particular order, and we want to sort some other way, we need to define how we want to do that. So there's a few ways. One of the things collections can do, is there's no, I don't want to do that yet. Let's just go ahead and define a comparator. So what's another, let's say, way of comparing strings? And this does lexicographic comparison, yeah? Length. So we could sort them by length. So let's say we want to do that. We're going to resort this thing. Okay. And this time we're going to use the second version of sort, the one that allows you to define a comparator. Now here comes some advanced-ish Java, where we're going to define a class without giving it a name. Let me just make sure I got the syntax right. Yeah, good. So I'm going to define a comparator for comparing strings. I have to do that, I believe. Now, what's a comparator? Let's take a look at the definition of a comparator. It's a class, or it's actually an interface, that has to be able to do this. It has to be able to take two objects and compare them. So it returns it as one method that it implements called compare that will tell us if one object is less than, greater than, or equal to its the other. So it takes these two arguments, O1 and O2, and it should return 0 if O1 and O2 are considered equal, and it should return a negative number if O1 is smaller than O2. It should return a positive number if O1 is bigger than O2. So let's do that. Implement that thing. So it needs a int compare string s1 string s2. Okay. And you said you wanted to compare by length, right? So how do we get the length of a string? Size, right? So we want to compare s1.size and s2.size. And we want, if the two things are equal, then should return 0. If s1 is shorter, then we should return a negative number. And if s1 is longer, then we should return a positive number. Is there an easy way to satisfy all of those things? Yeah? Minus, yeah. We'll just subtract the size of S1 from the size of S2. If they're equal, we get 0. If S1 is smaller, then we get a negative number. If S1 is bigger, we get a positive number. Okay. So now all we have to do is make sure that all of our parentheses line up. So we create this new comparator. That closes that. This closes the parenthesis on our call to sort. This almost surely won't compile. But, and this should return something. Okay, yeah, I know. Okay. Weaker access privileges was public. I thought that was the case. This should be a public method. That part is okay. And is size not what you use for strings? Length. Cool, so it compiles. Does it work? Let's see. So we sort again. We get Amy, Raj, Penny, Howard, Kripke, Stewart, Leonard, Sheldon. So indeed, they're sorted by length now. Okay. So this is another thing lists are useful for, is because they have an order associated with their elements, but it's not tied to any particular sorted order or anything. You can sort them in the order that you define or in the natural order and get what you want. So, you know, up here we had made this map that mapped these names onto numbers, and we wanted to sort, but not by name, but by number instead. So we take that whole thing, we copy it to a list, we then sort that list using a comparator that we define that compares those numbers rather than the names, and outputs them in the order we wanted. Yep.
What is that called when you're defining a new class besides the class?
Yeah, this is just called creating an anonymous class. It's kind of a yucky bit of Java syntax, but really what we've defined here is a new class. If you wanted, you could make a whole separate class that's called my special string comparator that implements the comparator interface for strings. And yep, then you don't override it, you implement it, because comparator is just an interface. So you're creating a new class that's actually empty, and you need to define, at a bare minimum, you need to define compare. Yep. Can you use a comparator in a priority queue?
Yeah, not this one.
Yeah, I mean, you can use, so we'll see there's priority queues. Well, we won't see, you can see. But these comparators, they're these simple classes that just define this compare function. You can use them in all the places where there's sorting. So in particular, when you create a tree set, for example, or a tree map, which are sorted sets and sorted maps, you can give them a comparator that tells you what order the keys should be compared in. Be careful. For example, if I were to use this comparator in a tree map or a tree set, then I would not be able to store two strings in that set if they had the same length. Right? Because if they have the same length, then they're considered equal by this comparator. They shouldn't both be in that set. So you have to look out for that kind of thing. Make sure what you're doing makes sense. Okay. Okay. So now you've seen the collections class. You have seen how to sort using the collections class. I think the only thing left for me to show you that might be useful for the assignment is the deck class. Or the deck interface. Which is implemented by the ArrayDeck class. Okay. Anybody remember what a deck does? Yep. It what? Yeah, so it's like a paper towel tube that has two ends. You can stick things in one end or stick things in the other end, and you can remove things from the end, but you can't reach into the middle of it and pull some random element out. You can't look at random elements. You can really only look at it from the ends. It's a generalization of all these other things, like a stack where you could only add and remove from one end, or a queue where you could only add in one end and remove from the other. So you don't need really explicit stacks and queues anymore. A deck can do all of the stuff that those can do. Yep. Can it do it as efficiently? A deck is generally, the current implementation of deck in the collections framework is a little bit more efficient than the implementation of a FIFO queue, but there are faster stack implementations, and there's a goodish reason for that. Okay, so I can do something like okay, so I've just created a deck and added some things as the first or last elements. So what's in that deck right now? Somebody want to tell me what the sequence of strings are in that deck? This is my name. Let's see. This is my name. So we added my at the beginning of this thing. We added name as the last thing. Then we went back to the beginning and added is, and then we added this. So we ended up with this is my name in that order. And if I want, I can edit that in this very restricted way. So remove this is and leave my name. Oh, I forgot to print it. So now it says my name is Pat. And if you wanted to be a little bit fancier, you could say save yourself. That. Okay. So the thing to know about decks and array decks is, well, a deck does its job efficiently, and because it has a very easy job to do, just adding and removing from the two ends. So you can trust that add first, add last, remove first, remove last, that's all efficient. So that's, for instance, something you can't trust with something like a list, because adding at the beginning of a list is not really so efficient. So it has at least two places in your assignment where you could use a deck to simplify your lives. Okay. Does anybody have any questions for me? Yep.
So, other than a deck, what is efficient at adding to the front?
Other than a deck, what's efficient at adding to the front? There is an implementation of list called linked list, which is efficient at adding to the front. The problem with linked list, I don't need to show it to you, it just implements the list interface. Very quickly, how a linked list works is it stores a list of elements, not as an array, but as a bunch of independent nodes. And each node contains a pointer to the next element in the list and a pointer to the previous element in the list. So it actually looks kind of like this. And it also contains the data that's supposed to be in that node. So adding to the front of one of these is actually pretty fast because all you do is create a new node and link it to the front. Adding to the back is also pretty fast because we just create a new node, add it to the back. But doing anything in the middle of one of these actually gets expensive. In particular, the things which are really cheap on array lists, which are getting the ith element from an array list, is expensive on a linked list because if I want to get some element here in the middle, the only way to get to it is either to start at the front and walk forward until I get to it, or to start at the back and walk backwards until I get to it. So get and set are not efficient in linked lists, which is usually why people use array lists. Yep.
How would that differ from the deck?
How does that differ from the deck? The deck doesn't even let you access elements in the middle. Deck just forbids it explicitly. Yep. Comparable is an interface that almost everything implements. So it does the same kind of job, but to be comparable, you have to implement something called compare to, and so that means you have to implement a method which compares yourself to some argument. That's what the comparable interface does. Comparators are a class that implement one static method or not a static method, but one method that compares two different things that are unrelated to the receiver. Yeah, so the comparators take two things and compare them that are not in the same class. Comparable means I'm something that's able to compare myself to other things in the same class as me. Yeah. Okay, so that's it. I'm not going to talk about the Java collections framework anymore after today. So if you've been staying away because of that, good. If you've only been coming here for that, well, sorry. Anyway, now you know everything you need for the assignment. It's going to be... It's going to be in a couple of weeks. I haven't set it yet, but probably something like 2 weeks.
Okay, so now when I try to set down the added into the tab,
What?
tab.
So it's not in your path?
Oh, no, I'm not setting it up. Down.
Okay. So then I suggest you go see one of the TAs during their office hours, or if you have a really specific question, post it on the forum.
Okay.
So I'm still confused. How do you run it on the kernel or because you do it, it does not work.
So you're running Windows, I guess, right?
I'm running Mac. It's Mac OS. That?
Okay. And that shouldn't be such a big deal. Do you have some version of Java installed?
When I do the compile it works, but when I call it Java, it's hard to do it.
Change the directory.
Okay.
So it wants a fully Java wants a fully qualified class
So if I don't want
the package names
so I just put it in change the voice. It isn't.
I mean, it's fine. It's fine. You just have to run it from one folder up. It's in that particular package.
Okay.
I'm actually wondering if you're gonna post the get it text file.
Yes, I'm going to post this file that we've been playing with for the last couple of classes. I'll put it on the coursework page.
Okay, thank you.
I had a question about running it through the command prompt or whatever. So I'm getting the typical Java C is not a recognized command and whatnot.
Yeah, so you're running Windows or
Windows 8.
Yep.
As well as you mentioned something about Java 8. Is it fine if that's installed? Do you simply avoid?
Java 7 or Java 8, either one.
So it's not a problem that 8 is installed? It's
It
just you
shouldn't
simply
be, no.
you should avoid it.
No, what you need to do is, if you want to use the command line, the first thing is you should be using PowerShell.
Yeah.
Second thing is you need to put it in your path. And there's a super annoying way to do that. You go, let's say, to Python the hard way. You will have to enter a command that looks like this. Everything will be the same, except instead of C drive Python 27, you'll have the full path to the Java bin directory. That'll put Java in the path in PowerShell's path, and then Java C and Java will both be in there.
Sorry, so you said Java bin directory?
To the bin directory of the Java installation. So you'll find probably in C drive program files, there'll be like Java and then several different things.
That kind of thing.
The JDK bin.
But in the end, I still need to navigate to like package where I extracted.
Yeah, you need to
I still need to
navigate to
navigate
the.
there
You need
and
to
then
go to
run
the directory where you extracted the stuff, and then run
it.
Java from
But
there.
after this should be fine. So I don't need to install Python as well or anything?
No.
So
You don't need
PowerShell is
to.
probably-
This is just the only place I remember that has this ridiculous setup you have to do under Windows to
Okay.
put things in your path.
All right,
Yeah.
thank you.
Hey, for DQ, I just had a question. Using the remove first and then add to last to cycle through the DQ to find a specific element, how
Yeah.
inefficient is that? Is it reasonable or is it not worth using?
I mean, are you doing this all the time to find a specific element? I mean, so in general, if you're looking for a specific element, then lists and decks and things are not the things to use. You probably want a set or a map.
Yeah.
So looking by examining everything is never the right way to do it. Yeah.
I just wanted to ask, because I just registered for this course.
Yep.
I'm from Computer Systems, actually.
Yep.
So I just wanted to ask if there's anything I need to know to get the assignment done, or
You need to know how to program in Java.
yeah, not programming Java.
Otherwise, I don't think so. Yeah. Professor who? I don't know who's teaching it. Yeah, I mean, it's just about programming in Java. So
All right. Okay. And what IDE are you using, or?
I'm just using the command line, but you can use
Okay.
any IDE that you want.
Okay. And
Just
when is the assignment due?
Probably in a couple of weeks.
All right.
So maybe a couple of weeks from Friday.
Thank you very much.
All right.